title is very broad, very general, and accordingly, instead of concentrating on details of one selected problem, I'm going to show you an overview of very different applications of discrete element methods to CI's dynamics and to breaking of CIs. This is the list of topics. It might be a bit misleading because I'm going to spend a lot of time on some of those things and just very briefly mention rigging. There will be just one slide on it, but I like this application, so I would like to show it to you. And as I said, these are very different examples, different problems, but what they have in common is the methods used to simulate them. Before I get to those examples, I will spend some time on the discrete element method itself, its components, equations that are solved, and so on, because this is something that decides upon the range of applications of those methods, the spatial and temporal scales that we can analyze, limitations and capabilities of the models, and so on. But first, in order to put the subject of my talk in a wider context, a few words of introduction on continuum CI's models. This is something that Ken also mentioned in the introduction to his talk. At large scales, we use continuum CI's models to simulate CIs, which means that we assume that we can treat the ice as a continuous mass rather than as a material which is made of a lot of small elements. And we use the equations of conservation of mass and momentum, which are used to obtain ice concentration, ice thickness, and ice velocity. These are example maps of obtained with one of the most popular large-scale CI's model size, in this case applied to the Arctic domain. In size and as in most large-scale CI's models today, we don't use just average ice thickness. We have a ice thickness distribution, which means that even though we do not know how different sea ice thickness classes are distributed within grid cells of our model, we know what is their contribution to the total surface covered with ice. And this brings us to the very important assumption of continuum sea ice models, namely that the grid that the cell size of our model is much larger than the characteristic size of objects that we are analyzing, ice flows, cracks in the ice ridges, and so on. This is assumption underlying the rheology models used in large-scale sea ice models, and so on and so on. And when we think of ice as being made of a lot of ice flows, and we have a lot of processes taking place at the levels of individual ice flows, then we may ask what happens at larger scales if those processes simply cancel out and we may disregard them. That's one possibility. Or if we have larger scale effects of those small scale processes that we have to take into account in order to obtain a valuable solution of our model. And this can be done, for example, by introducing the flow size distribution to our model in a way analogous to the ice thickness distribution, which is used for many years now. It is an approach that works provided that we are able to formulate source terms for the equation describing the evolution of the flow size distribution, and then we also that we are able to modify the existing source term in order to take this information about the flow size distribution into account. This is something that Chris Horvath is going to talk about today in the afternoon. Just to illustrate the point with a very, very simple example, one of the very characteristic properties of granular materials is a tendency to form clusters of particles, molecules, grains, whatever we call them. And we often see clustered ice flows on the sea surface in satellite images, for example. There are a lot of mechanisms that may produce clusters of ice flows. Some of those mechanisms are related to the very nature of granular materials. These are very universal mechanisms related simply to the fact that the restitution coefficient of granular particles is lower than 1. Some kinetic energy is lost during collisions, and this produces this tendency for colliding particles to stay together close to each other. But in the case of sea ice, we of course have a lot of different mechanisms related to waves, surface currents, Langmuir circulation, and so on. Whatever the mechanisms, once we have those clusters on the sea surface, they might influence a lot of processes that are taking place. For example, it might make a difference for wind wave generation in areas partially covered with ice. If we have ice flows randomly scattered all over the sea surface, or if the ice flows are clustered and we have large open water spaces between them at the same ice concentration, so at the same larger scale characteristic of sea ice. So this is an example how the subgrid scale distribution of ice flows might influence what is going on at larger scales. And it is easy to qualitatively describe a lot of similar processes and effects. In most cases, we simply don't know if they are important and if we should try to include those effects in our models or not. We often simply don't have enough observational evidence for that. It is very hard to get that evidence. So the question is, what kind of processes are affected, dynamical ones, thermodynamical ones, where those effects are important in the marginal ice zone, or when ice is transported through straits or channels, and so on. We may also ask if only sea ice is affected, or perhaps also the upper layer of the ocean or the lower atmosphere. As I said, in many cases we simply don't know at the moment, and on the one hand we have sometimes a lot of evidence from research or granular materials in general, so we may suspect that ice will behave in a similar way. On the other hand, there are a lot of unique features typical for sea ice that make it very different from other granular materials. One is the very wide size distribution of grains of ice flows in this case, which is often a power law and covers many orders of magnitude. Another is the fact that this is a granular material which is at the level of ice flows something close to two-dimensional, which is floating on the surface of a liquid. So this is something that might modify those general types of behavior of sea ice. And the examples that were on the list on the first slides that I'm going to show you today were obtained with a discrete element sea ice model that I developed. It's called design. The GN don't mean anything. It's discrete element sea ice model. And some of these examples were obtained by myself, some were obtained by others with just some technical support from my side, or some implementation of new features that these other persons wanted to have in the model. I'm very grateful to all those persons, because it really helped to move the things forward, to find bugs in the code, and it was very productive. But first, about the model itself. As every discrete element model, it is based on grains or particles, doesn't matter how we call them. In this case, they are disc-shaped, and they might be connected with bonds, in this case, with rectangular cross-section. Each element in the model, each grain and each bond may have its unique material properties and different sizes, so which means that we may, for example, simulate ice cover which consists of a lot of different ice types, thicker ice, thinner ice, and so on. And we may apply the model in like a standard granular material model without the bonds. In this case, we prescribe a certain size distribution of grains which are identical with ice flows in this case, and study the dynamics or very simple thermodynamics processes like lateral melting of those ice flows. We may change their sizes. Or when we use the bonded version of the model, we may use grains and bonds as building blocks of ice flows. In this case, we may have irregular shapes of ice flows. We may also simulate the evolution of the flow size distribution if we allow for the bonds to break. And again, as every DEM model, this one solves the momentum equations for each grain in the modeled system. These equations are very general. We have to formulate forces acting on the grains from the ocean and from the atmosphere. Very broadly, then can be divided into surface and body forces. And very importantly, we have two types of interactions between grains. The first one is through a direct contact when the grains are touching each other, and the second type of interaction is through bonds connecting grains. We here sum over all neighbors or all partners of a given grain in order to calculate the total force acting on that grain. I won't go into much detail because there is no time for that, but as for the first type of interaction, the contact mechanics, it is relatively straightforward to write a general expression for the interaction force. It has two components, normal and tangential to the plane of contact, this one, and each component in turn consists of two terms. The first one is related to the so-called overlap between grains. It's in fact not an overlap, but the elastic deformation of those grains, which is marked here with delta. And the second component in both cases is related to the relative velocity of those grains. So this is the easy part. The most difficult, the more difficult one is to find those four coefficients here, because they certainly depend on the material properties, on the elastic modulus of grains and so on. But also, if we have a material consisting of grains with very different sizes, it makes a difference, and it makes our model nonlinear, because those coefficients then are functions of the relative size of the disks and of the overlap. So together with this delta here, we have dependence on delta in the coefficients. And these values are very different from the net material properties that we observe at larger scales. So usually we have no clue how to which values are correct ones before we run several computations and calibrate our model to a certain application. To this general formula we may add another terms specific for any application, in particular rolling resistance or rolling friction, which is something that prevents the grains from rolling along the perimeter of each other, and we might have cohesion and some other interaction mechanisms. As for the other, the second type of interactions between grains, those that are transmitted by bonds, I didn't write the equations here. There's a number of them describing again the normal and tangential force, and in the case of bonds we also have the bending and twisting moment. Plus we have to specify criteria describing how the bonds break if we want to include breaking in our simulation. In most models these criteria are based on stress acting on bonds, which means that we prescribe for each bond its compressive, tensile and shear strength, and if the stress acting on that bond exceeds the maximum value, then the bond breaks. And the last thing is what it really means that the bond breaks. In a great majority of DEMs, the material is treated as something perfectly brittle at the grain level, which means that the stress is reduced from its maximum value towards zero from one time step to the next, which is not very realistic, of course, and apart from being not realistic, it often introduces spurious perturbations to the model. So we have like wave propagating from the breaking location that induces breaking in several neighboring locations, which is not something we really want to have in our model. So in my CI simulations I use some softening factor which effectively leads to the breaking event being not infinitely fast, but taking place over a certain time span. So there are, as you can see, there are a lot of parameters to play with when we try to set up the model for any particular application. Fortunately, some of those parameters have only minor influence on the macroscopic behavior of the model. It depends, of course, on what aspects of the solution are interesting for us. Another thing which people are very often asking me is about the shape of the grains used in the model. And the equations all very often begin with, but the ice flows are not circular, so why don't you use, for example, polygonal particles in the model? If we would make a statistics of different DEM applications, then the great majority of models use spherical geometry of grains, and the basic reason for that is very practical, computational one. It is much easier and computationally much more effective. We don't have to care about all possible configurations of interacting grains or types of overlap, which makes our code faster. Another reason is that, again, it depends on what aspects of the solution are interesting for us, but many effects that are related to the angularity of grains and to their irregularity can be simulated by applying rolling resistance to our model. So this rolling resistance is sometimes used as a parameter simulating some aspects of irregularity of the grains. It works in practice very well. And in the case of CAs, there is one more thing that we have to keep in mind. These are two satellite images that illustrate the problem. These are MODIS images from two following days in May, and they show the strait between Greenland, which is in this part of the image, and the Canadian archipelago. And as we can see, the ice flows are definitely not circular, they are polygonal. But when we build our DEM model with grains like those we can see in this image, then sooner or later the flows get stuck in the channel, and we may apply whatever wind and current we want. They won't move. We will obtain very high stress levels, unrealistic, because what the real sea ice does in this case, it breaks into smaller ice flows. And it is not at all obvious how we should formulate criteria for decomposing our large polygons into smaller ones without making some very arbitrary decisions about this is, I think, one of the questions that Don wanted to have answered during this week, the rules that break a large flow into a lot of smaller ones. So in a DEM, it is sometimes easier and better, I think, to make our irregularly shaped ice flows from smaller elements, smaller grains, much smaller than in this drawing here. I'll just put some circles on it. But if we make them sufficiently small, they should not influence much the behavior of the model, and we should be able to simulate breaking of these ice flows into smaller ones. So now to the application examples that I mentioned in the beginning. The first one is related to the jamming phase transition. This is something very characteristic for granular materials, and under isotropic compression, this is a process which is very well studied, and we understand well how the particle packing fraction influences the course of the phase transition, how the material changes from flowing state with very low stress levels to a solid-like state with levels that might be a few orders of magnitude higher. And recently, a number of new jammed states have been described. Most of them occur under shear deformation of the material, as opposed to isotropic compression. And when we look through the literature or go to conferences on granular materials, there are a lot of discussions about whether those jammed states are really jammed or not, if they possess all features of the jamming phase transition or only some of them, and if this is a matter of definition, of course, a bit, but some years ago I analyzed numerically the shear jamming transition in granular materials with very wide size distribution of grains. I had sea ice in mind, of course, but it was a very general study, and it showed that if we compare the behavior of a material like this with similar material with grains of similar sizes, then it changes a lot in terms of how the transition happens and how strong shearing we have to apply to the material to obtain jumped or jump-like states. But there is a recent very interesting study which is directly related to sea ice and jamming, or more precisely it is related to melange of sea ice and icebergs that can be found in many fjords around Greenland, for example, fjords which have marine terminating glaciers at their ends. These are two photographs from Jakobshavn Glacier as an example. And this is a study done by Alex Robol using the design model. The motivation were some observations from these fjords and hypotheses based on those observations. In particular, what is observed in Greenland in many fjords is that there is a coincidence between the iceberg calving and melange breakup, in the sense that in spring, when the sea ice between icebergs is melting or breaking, we observed rapid increase in iceberg calving rate. And the related hypothesis is first that this melange of icebergs and sea ice might exert a buttressing force that suppresses calving in winter when sea ice is thick. And the related hypothesis is that as we observe thinning sea ice in recent years, the buttressing force may get lower and we may observe stronger calving in the future. Not only in the summer period, but also in winter, when at present we observe almost no calving. And this is a situation which is really hard to model with continuum ice models, because the fjord is very narrow and it is hard to calibrate the model for this mixture of sea ice and icebergs. The study of Alex is the first one in which a discrete element model was used for this purpose. The configuration is very simple. We have an ice fjord, straight one, or in another version with some narrowing in it. In this case, the grains of the model represent icebergs. They look normal size distribution like that observed in the Jakobshavn Glacier. And sea ice is not shown in those images, but it is made of bonds connecting the icebergs. And Alex did a number of simulations, either with slowly advancing glacier terminus, so this left side of the computational domain, or with rapid calving events. You can see this calving, this new iceberg entering the fjord here. And this is where jamming comes in. Again, it cannot be seen in this animation because it does not show sea ice. But this is yet another flavor of jamming, which is called impact-induced jamming. Again, it is disputable if it is a real jamming phase transition or not, because it is very short-lived and it propagates through the material as a kind of a shock wave. What it does, if it is sufficiently strong, it may break sea ice between icebergs, which makes the whole melange more vulnerable to following calving events. So the simulations suggest that it is something that is sensitive to previous events. And another thing that Alex did was to compare the model results with GPS observations from calving events in Jakobshavn Glacier. Here you can see the speed of icebergs in function of the distance from the glacier at several time instances after the calving event, here from the model, here from observations. I think that if we consider how very simple the model configuration is, the agreement is quite good, both in terms of the speed of the jamming wave, which propagates along the fjord, as and in terms of speed of individual icebergs. And this good agreement motivated Alex to do some sensitivity study with varying sea ice thickness and see how strong is the force acting on the glacier, which, as glaciologists say, is important for shutting down calving or not. According to calculations, this is something close to 10 to the 7th of newtons per meter of the length of the terminus. And when we set up the model with thick sea ice, we obtain forces above this limiting value, and at least the model suggests that when we lower the sea ice thickness to 1 or 2 meters, we might get to values that are much lower than that. So this is an example how the granular nature of what is going on in sea ice and iceberg melange in a fjord influences what is happening. Again, once more, we have this sensitiveness to previous events because they modify the properties of the melange. And we have the geometry of the fjord, when we go back for a moment, which also influences the propagation of the shock wave because it tends to slow down in places like this, and this modifies which areas have broken sea ice and or not. Another example includes a lot of what-if questions and speculating, philosophizing, and the idea is about relationships between the deformation of sea ice flow size distribution, and flow shapes. This last characteristic is only seldom analyzed, and at least not in the context of the processes that are taking place in sea ice. And this is a few of existing ideas, some of them existing for a long time, taken together, and we might try to treat them as elements of a puzzle and try to see if they fit together. The overall idea is to treat the evolution of flow size distribution and flow shapes as a kind of optimization process taking place in response to forcing acting on ice. So this is a different idea to that, for example, of random breaking models, like are used sometimes to explain the observed flow size distributions. And as I said, the elements of this idea are there. Even if when we take the seminal paper of the flow size on the flow size distribution by Rothrock and Thorndike from 1984, they noticed that ice flows are densely packed on the sea surface. They entirely cover sea surface and have fractal properties, and they use the analogy to the Apollonian gasket to describe the properties of ice flow sizes on the sea surface. Apollonian gasket is constructed in such a way that we put smaller and smaller circles between larger ones, and we do it in a way that each circle that we place there touches exactly 3 neighbors. And this number 3 is very important here in this context because it is related to the response of a material constructed as an Apollonian gasket to deformation. We may try to imagine that we start to shear the material which is constructed like this. And let's suppose that those two largest circles start to move in opposite directions, roll in opposite directions, so we have a rolling contact between them. Now when we look at the third one, it doesn't matter in which direction it starts to rotate, we always get one rolling and one frictional contact. Here F means friction, R means rolling. And we might continue this process to smaller and smaller circles. The story repeats itself. We always have triangles, smaller and smaller one when we go down the scale with two rolling contact and one frictional contact. What this means effectively is that the Apollonian gasket, or a material made as like an Apollonian gasket, when it is sheared, it has a certain resistance to shearing, and it is mostly dependent on those frictional contacts because it requires larger forces to move the grains relative to each other at those frictional contacts. And this is related to this number of 3 that was used in the construction of the Apollonian gasket. These are called minimal cycles when we analyze the structure of granular materials, which are simply loops joining the grains that touch each other. And if the loop size is 3, 5, 7, and so on, we always have some frictional contacts between grains. It's not possible to rotate them all in such a way that we have only rolling contacts. In turn, when the loop size is even, 4, 6, and so on, it is possible that the grains move in a way that we have only contacts of rolling type between them. What is also important is this exponent here. In the Apollonian gasket, we have a fractal grain size distribution with the exponent that can be calculated. And this will be important in a minute when I move to a material which is built based on loop of sizes 4. This is called space filling bearings. And there are lots of papers on that, but mostly by Hans Herman and his group from 1990s and from the last couple of years as well. They developed a lot of very fancy algorithms that allow for constructing space filling bearings with arbitrary loop sizes in 2 dimensions and in 3 dimensions. Some of them are very regular ones, some are based on random placing of grains in space. And they have different exponents if we look at the grain size distribution. And what is very interesting is that it is something we can find in nature. For a very long time I thought this is just a nice geometrical exercise. Then I learned that there are models of shear bands and seismic gaps that use this analogy of space filling bearings to explain what is going on there. And then I learned, that's why I put an exclamation mark here, because I find it sort of amazing that it is possible to measure it really. So there are measurements from seismic gaps which use remnant magnetization of different pieces of rock, and those measurements show that the rock really is moving like in a space filling bearing. And there are similar studies on landslides and slow avalanches. And again, we can use this exponent of the grain size distribution here as a kind of an indicator what type of arrangement of grains we have in space, because with a given exponent here we are not able to obtain all kinds of space filling packing. When we use a DEM model to study what is going on, as I said, the model that I'm using is based on circular grains, but we may use rolling resistance as a kind of trick to simulate angularity of grains, and we may modify it during the simulation to sort of make our grains evolve from angular to circular in shape, from having high rolling resistance to low one. And these are just two snapshots because there is no time to go into more details on that. But when we start the model with grain, with a certain grain size distribution, it evolves naturally towards a kind of packing that is characteristic or related to this kind of grain size distribution that we selected. This simulation was done for grain size distribution typical for Apollonian gasket, and the model evolved by itself towards a state when we have roughly 2/3 of contacts of rolling type and 1/3 of frictional type, provided of course that the rolling resistance is very small, which means that the grains are close to circular. So back to this puzzle from which I began. This is an idea which is well developed in studies of fracture zones in rocks or calving glaciers. I think it could have some significance for sea ice as well. To summarize it somehow, the first point is that during initial fracture, angular grains are produced, and their size distribution very strongly depends on the conditions under which this fracture happens. So in sea ice we might have initial distribution of ice flow sizes like this when the ice is broken by waves, and we have a dominating flow size. There are some recent numerical results that show that we have flow size distributions close to normal Gaussian ones in this case. And then the power law, the white size distribution of flow sizes develops under combined compression and shear, which is something typical for the inner marginal ice zone. And together with the power law size distribution, we have also gradual rounding of the shapes of the grains. So this is something that can be studied with DEM models. I guess it would be hard to find observational evidence from the field for that. This is this one slide on ridging that I mentioned in the very beginning, and again this is a study not done by me but by Jeffrey May. He's a PhD student at the joint program of MIT and Woods Hole, and he's interested in studying Antarctic ridging. It is a study begun just 2 or 3 months ago, but still Jeffrey agreed that I showed this animation. As you can see, there are some not very realistic effects still, which are related to the elastic modulus of the bonds connected. So, but still, we have some rafting and some ridging process. The whole application of the model is based on the fact that, in fact, that it is two-dimensional, but it does not recognize which dimension is which. So, if we specify buoyancy and gravity forcing along one of the axes, we may treat it as a as a vertical one. So this is a study of ridging in one vertical, one horizontal dimension, and I'm really very interested in how this work will develop in the future, and what kind of insights on ridging we will get. And the last example is something on which is it the signal or someone calling you? Okay. Something that I've been working on recently, a coupled hydrodynamic sea ice model, which includes the sea ice module, which is a simplified design version, so to say. It is a discrete element model, and the wave module, which is based on the hydrodynamic model NH wave. So this is the cartoon with the idea of the whole model. There was a two-way coupling between the DEM and the wave model. The equations, I won't explain them, but these are standard equations used in the hydrodynamic models, and simplified equations of the DEM model. As I said, we have those boundary conditions that I exchanged at every time step. And to start working with the model, I wanted just to see if the whole idea is correct, and if we can couple the DEM model of the type that I'm using to a hydrodynamic model. So I wanted to run very simple configuration. You can see it here. We have a continuous ice sheet, and we generate waves with prescribed characteristics inside the model domain, and we let them propagate into the ice and break it. So this is a very simple problem, which was studied by Vernon Squire and his colleagues in 1990s, and their models clearly show that the ice thickness is the parameter that decides on the size of the ice flows generated by wave-induced breaking. And still, when we take different models and parameterizations of this process used in models, we also find half wavelength as the characteristic size of ice flows. And I wanted to, this is a perfect case for for studying the as a first case to run with a model, because it is relatively simple and still the results might be quite interesting. I won't describe what is in this figure, but when we look at the flow sizes resulting from simulations with different ice thicknesses and different wavelengths, we really see that ice thickness matters, and it changes the flow sizes that are produced by breaking. And when we change the wavelength of the incoming waves, we obtain almost the same flow sizes. So this is a very different model, but produces results that are in agreement with those of Vernon and colleagues. And conclusions, I've got just two. The first one is that, okay, it's my very subjective conclusion. The second one is that it would be nice to have data to validate the results of the DEMs that we obtain, which is not an easy task. And I learned that last year when I took part in a laboratory experiment of ice breaking by waves, when the ice was very uniform and the waves were regular and under controlled conditions. We obtained ice flow distribution like this, which means that we were not able to eliminate all those additional factors, influences ice breaking that in these experiments we wanted to eliminate. So we had very wide flow size distributions. this shows how difficult point 2 might be. It was longer, I think. Sorry about that.
Thank you much, Agnieszka, for a fascinating talk. Yeah, has everyone looked a bit, and I'm not sure what the lunch arrangements are. So I noticed we've got lunch and we've got half an hour for discussion. So I think maybe we can pick up questions about this. I certainly have about 10 questions. So we'll pick up some questions in that period now. So if we now go to lunch, lunch is in Woodson Court, so it's basically next door. So if you're out of the building, turn left again, and that's where you are. You're there.